So you're using 0.5, 50% chance either way. They take the middle of the road. Always round up. And then they ask you, if they gave you a P and you found your Q, what would happen to your sample size? Now, normally if you know your P and your Q, you need less, because 50-50 is the middle of the road. It would probably give you the highest that you could get. What happens here is this. This is 0.5. This is 0.48. They're very close, aren't they? It's almost 50%. So it did give us a little bit more fine-tuning. Simone?
I got those numbers, but it was like 6 decimal. 0, 0.
6 decimal?
Yeah. I don't know about but like, look, like if you look, I got all the same numbers, like in the sequence, but it's just like.
Did it have an E thing? Like, was it a scientific notation number? Did it have E
No,
before?
it was those exact numbers.
But your decimal. Yeah, but what I'm saying was it like this? 60025, and then it had E to the third, E3. I can't have E3. I wouldn't think it would have E3, but try it in your calculator again.
Right now?
Yeah. Okay, now normally when you know your P and Q, your sample size is smaller. You don't need as many. These require a lot of a higher sample size than our Z-score things did. But normally if you know your P and Q, your sample size should be a little bit smaller, a little bit more controlled. Something just must have went in wrong, right?
Yeah, I did 0.4.
You did 0.4. Oh, that's why. So that made that be a really small number. Yeah. Okay. Remember your 4% and flip it to a decimal, move it 2 places. The second one that they did here is probably a little bit better to see, because here they went, you had no preliminaries, so you went 0.5, 0.5, but here we went to 0.28. See the decrease in your sample size? It's a lot more noticeable.
What do you do for when it says compare the thing? You'll say the sample size is smaller?
The sample size is smaller when you know preliminary information. That's all. You should get more defined with preliminary. 50-50 is the highest, because that's like the middle of the road one. So normally you know one way or the other. Now the reason we didn't see a big jump in the other one was because 0.48 was very close to 0.5. So we didn't see a very big jump in that one. And the last one, the last two, they gave you a chart with the percentages for United States, France, Great Britain, and Spain. They gave you a chart for those. Those were your P's. You had to do this 4 times. So they gave us an N so that we knew what the N was for each one. So for instance, for the United States one, you look at your chart and it was 0.69. Said they would consider travel to be safe. And then you worked it out of 1,044 adults they surveyed. So they gave you the information for each one. Their goal in this was not just having you do this 4 times, but for you to be able to see the answer to 22. That your confidence intervals can overlap. So even though they looked like they were all different, when you lay them all out on a line, they overlap a little bit. So they're saying, the way they asked it was determine whether it's possible that any of the population proportions that you found for each individual country will be, or at any point will be equal, and explain why. So is everybody okay with finding the individual parts? And you can absolutely use your calculator. The test, you just have to do them all separate. So you go to stat, you have to find your 1 proportion Z interval, wherever it happens to be on yours. Your X, now you have to figure out 69% of 1,044. So just do 0.69 times 1,044. This is where you can't put your decimal in. So we'll go with 720. Just round it. You can't put a decimal in here. Out of 1,044. Confidence interval 99. This is fine to do all four of these on your calculator. It makes more sense. When you round it to 3 decimal places, you'll also find this is really almost to your 0.69. Yes. Oh, okay. So you could do all of yours on your calculator step. Can everybody use the calculator for this?
I don't know.
You don't like it?
I don't like
Okay.
I never liked
Alright.
using the calculator.
Okay.
I always liked doing calculator.
I always get half the kids use the calculator and half don't. Right?
Yeah,
They gave us the N in the word problem right up here.
But it's always like, will it always be like that? Like one
No, normally it's just like one problem. You surveyed 4,000 people, 800 said yes. But this one they were comparing, guys, they're comparing 4 countries. And they asked 4 different countries, all different amount of people that they surveyed, and they got their results, which they showed in that chart. 69%, 72%, 62%. If you look at their p-hats, are they that different? Are their p-hats that different from all the different countries? Yeah, they're all pretty much between 60 and 70, between 62 and 75%. They're all fairly in a good zone. So therefore, their intervals, because all their ends were also pretty close. They were close to 1,000, about, So here's the big thing. When you compare them, there's a place where they overlap. Now, here's France. France is my red. Spain is my orange. See it? Great Britain is the blue. And the United States is green. Do you see the place over here where they overlap? So there's a part of the population that they say is equal, or they're pulling from the same interval. And when we look at them, we don't see it because normally you're catching like the first part of it or the last part of it. But when you lay them out on the number line, they overlap. They slightly overlap. So I think this is what they were getting at by having you do all 4. Good? Does everybody understand these? Okay? Now, could I move it where? Table out here yesterday. So for this part, we have the population versus the sample. Remember, we make an inference about our population based on our sample. So we're going to make an inference about your population variance based on your sample variance. We're going to make an inference about your standard deviation of the population based on your sample standard deviation. Now, this series uses a bunch of formulas, which I will always give you the formula. And it also uses your chi-square is used a lot when you have like very, very small differences. You know how small your standard deviation is compared to your mean? Your variance is small. Well, in manufacturing, it is necessary to control the amount that a process varies. For instance, an automobile part manufacturer must produce thousands of parts to be used in a manufacturing process. It is important that the parts vary little or none at all. How can you measure and consequently control the amount of the variation, which is your variance, in these parts? We again start with a point estimate. For our population variance, we use the S squared. For our population standard deviation, we use the S. Now what this means is this. If I make a car, I'm making the car engine, and I have all these little bolts that have to hold your car together, right? What happens if the bolts don't fit in the car? Well, what happens if the bolt is too small for where it has to hold your engine together? What's going to happen to that? The engine's going to come apart, nothing's going to hold it together. What's going to happen if the bolt is too big? It won't fit in, right? So, and you know how big a bolt can be? A bolt can be really small, it can be a little larger, depending on different sizes. So you have to control how much that bolt varies. And it's extremely important that it fits exactly, otherwise your car is going to fall apart on you. So when we control something that has very little variance, you can only allow very little variance for that little screw, we use a variance or a standard deviation. A lot of the times they use the variance, which this is the only time you really need our variance. Usually we just use your standard deviation. So we want these things to vary just a little bit, very small amount. So we have the same kind of concept. We're making an inference about our population based on our sample. And what we're going to do is we will find our variance information, and then we will take care of our standard deviation from there. Now, the chi-square works very, very different than your normal curve. It's a series of curves again. It goes based on the degrees of freedom. If you look at your chart, you can see degrees of freedom along the left-hand side. It works on the degrees of freedom. But what happens? It's n minus 1. Yeah. So what happens here is, and I've got a better chart over here, and I'm going to put this in your notes. Now I'm stuck. If you notice, this starts at 0. Your normal curve has negatives and positives. Negative standard deviation to the left, positive to the right. That doesn't happen on this guy. This guy goes totally to the right here. And where your z-square is your area to the left, this one is your area to the right. So it works very opposite than your z-square. Excuse me.
It's not running because the laser is not.
Well, now it just clicked back on. Well, it clicked back on for me. It was I lose it every once in a while. It's red. Now, we call this little guy a chi-square. It's really kind of simple when you use it. N is how many in your sample. S is your sample standard deviation squared to be your sample variance. And sigma squared is your population variance, or your population standard deviation squared. Okay? All of your chi-square values are greater than or equal to 0. They're all positive. Whereas your z-square went negatives and positive, this is always to the positive side. There are a family of curves. They use the degrees of freedom n minus 1. The area under the curve still always equals 1. And they're all positively skewed. They're all skewed to the right, to the positive side. None of them make a normal curve. This is the only time we work with a non-normal curve. We work with the degrees of freedom, and therefore they look like this. And our goal, you know how you found your z-score and your t-score and you found them to be exactly the same because the curves were symmetric? These curves are not symmetric. So when we find the two values, they will be two different values because your curve is always positively skewed, and your curve always goes from 0 to the positive, and they always go with the skew. So you're going to find your two values using your table, but we're going to find two separate values. It's never going to be a plus or minus z. It's never going to be a plus or minus t. It's going to be called a chi-squared right and a chi-squared left. We're going to find those values in your table 6. Okay? And we're going to work off of those. It's really not that bad. It looks much worse than it is. But you have to remember the one thing. This is the area to the right. Area to the right. Goes against what we normally do. Your z-score and t-score have always been area to the left. This guy is totally different. Non-symmetric, from 0 to infinity, and it's area to the right. And if you look at it, you know how in the z-score they always show you the shaded to the left? Look where they show your area to the right. And we have a little bit of a trick in finding this. Obviously, when we do this, this has to be the smaller one, and these get higher. the right one has to be the larger one. Okay? So we're going to kind of cheat a little bit when we do this. Do you have to memorize these formulas? No. But doesn't this look real close to your inverse norm formula? Looks real close. 1 minus 0.95 divided by 2. So, left and right. But what happens is they kind of work opposite of what you would think. Because this time your area is always to the right. But so that we don't get bogged down by that, let's take a look at this example. You want to find your critical values of your chi-square right and your chi-square left for a 95% confidence interval when my sample size is 18. If my sample size is 18, what's my degrees of freedom? 17. Now, here's the problem. Here's your degrees of freedom. If you look across the top, they look a little strange, don't they? I never saw 0.995 used as my confidence. We only use 0.95, 0.90, 0.80. I never saw those used because they're not your confidence interval. You're going to take your confidence interval and you're going to do this. 1 minus c divided by 2. 1 minus 0.95 divided by 2. Tell me what you get. 0.025. Now, the other side says 1 plus c divided by 2. So 1 plus 0.95 divided by 2. Tell me what you get. 0.975. Your areas always add up to what? 1. So here's a little shortcut. We're going to do something that's similar to us because we like to keep something that we're familiar with. We're going to do this. 1 minus the c divided by 2. We're going to take this guy, then we're just going to subtract it from 1. We don't have to do this part. We don't have to worry about who's left, who's right. So I'll explain it in a minute. So this is equal to 0.975. Those are the numbers that you find across the top of table 6. So look at table 6. You see those numbers? Now, follow your degrees of freedom for 17. Follow 0.975 and 0.025. Do you see your chart is symmetrical in the chart? If you put a line down the middle, you see 0.90, 0.10. If you go out, 0.95, 0.05, 0.975, 0.025. Do you see like a little, you can make like a little rainbow thing down the middle? Aaron, you didn't look at your chart. You can't shake your head unless you looked at your chart. Here, look. Don't these guys add up to 1? Okay. Don't these add up to 1? So when I'm looking for a 0.90, my counterpart is 0.10. That's halfway in there. When I'm looking for 0.975, look where I find it. Equal distance over here to 0.025. That's another way to find it. So find me your two values. You're going to look in your chart. Degrees of freedom is 17. The top's going to say 0.975 and 0.025. Find me your two values. So give me one of them. Okay, give me the other one.
30.191.
191? Okay, now, guys, listen to me. If you don't get this part, you're never going to understand this. Watch how easy this is. I don't care who's left and who's right, because who's smaller? Of these, who's smaller? Ah, so this guy is my left one. This guy is this guy. Then this one is my 30. So, what I'm trying to tell you is, you don't have to get hung up on your formulas, which one is right, which one is left. All you have to do is what you know that you've been doing. 1 minus c divided by 2. Isn't that what we've been doing? So then we just subtract it from 1, or we look at our table, and we find where it's symmetric across the middle, and that would be its 975. We look up those two values. the smaller one has to be the left one. This is the chi-square left, and this is the chi-square right. The left one has to be smaller than the right one. Makes sense, right? Okay, we'll do another one together. Don't get hung up on the who's right and who's left formula. I don't even use those. Something that's familiar to you. Okay, let's try another one together. I want everybody to start out like this. Just make me a curve that looks like this. Make me an X2L. Make me an X2R. We need to find where your left is. We need to find where your right is. We have a 90% confidence interval, and we have a sample size of 30. So what's our degrees of freedom? 29. We're going to take your confidence interval, we're going to subtract it from 1. And we're going to divide this by 2, like you normally do for your inverse norm. What do you get? This is normally my area to the left in the z-score, but this is my area to the right in the chi-square chart. But that's okay. I'm going to take this guy and subtract it from 1. So I need to look up these values across the top when my degrees of freedom say 29. We did your inverse norm thing. Normally you say 1 minus 90 divided by 2. Usually it's your area to the right, to the left. Your chi-square is your area to the right. However, we're not going to worry about that. We're going to just find your two values. You always have to have two values. They're never the same. So, we did. No. Just this side divide by 2. And find this. These two have to add up to 1. So find me degrees of freedom 29. And find me 0.05 and 0.95. And just write them here. Thanks, Mariah. That's 1. 42.55. Now, thank you, Mariah. The 05 one. Okay, listen, guys. Okay, which guy of these has to be the left one? 17. This has to be my left. This has to be my right. That's how easy this is. So, same kind of process. We took your confidence interval, subtracted from 1, divided by 2. We don't care that the area is different. We're just going to take those two values we need to add up to 1. Find the two pieces. The one on the left is always the smaller one because it goes from 0 to positively skewed, so it's to infinity. There's never a negative number here. This is a non-symmetric curve. They're all skewed to the right, to the positive side, so we always get from this end of it. Okay? All right, I'm going to have you guys try some.
But if it's so easy,
It is so easy.
so why do we have to practice?
Well, because I need you to know this like this.
Come on, come.
Okay, so I need you to do number 4, number 6, and number 8 on page 334. 4, 6, and 8. All you're doing are finding me these two values.